Hello everyone! In this video, we will explain three different uses of matrices. We will start by explaining the adjacency matrix. Then we go on by explaining the transition matrix, and the last use of the matrix that we will explain today is the population matrix. We presume in this video that you already know the basic operations of matrices. Each time we make an exercise while we are explaining some theory. Let's go! An adjacency matrix is a matrix that shows if a node of a graph is connected to another node or not. Here you see a sort of scheme. We call this a graph. We will transform this graph into an adjacency matrix. We start this exercise by drawing the frame of the matrix. For this, we look at our graph. We see that our graph has 5 different nodes, which are connected with each other. We have a node A, B, C, D, and E. These are 5 elements. We have to make sure that we find every element in a row and a column. Because of this, we have a 5 by 5 matrix. Here you can see the 5 by 5 matrix. We write the letters on top of every row and beside every column. That will make it easier when we exercise. Sometimes we can see a little arrow on the connection between 2 different nodes. This arrow tells us that there is a one-way connection. In our graph, we see, for example, 2 connections from A to C. But on one of the 2 connections, we see that little arrow. This means that this is a one-way connection. It means that we have a connection from C to A, but not from A to C. Before we start filling in our matrix, we need to prepare our matrix a little bit more. On top of the letters from our rows, we put the word from. Beside the letters of every column of the column, we put the word to. For example, here we will find the amount of connections between B and D from B to D. Now we can start filling in the matrix. We start with the element on the first row and in the first column. In this exercise, we will be looking for how many connections there are from A to A. Like we see in our graph, there is no connection, so we write down a 0. In this exercise, we will start by filling in our entire column A before we move on to column B. We recommend working in a structured way so that you won't lose sight of what you already done and what you still have to do. Now we look at how many connections there are from A to C. We can see 2 connections, but now we have to pay attention. There is a one-way connection from C to A, but not from A to C. So over here, there is only one connection from A to C. For that, we write down a 1 in our matrix. We can see a one-way connection from A to D, like this. So we put down a 1. There is no one-step connection from A to E, so we write down a 0. In the second column, we have to note down every connection we find that starts in node B. We cannot find one from B to A, so that gives us a 0 in the matrix. We also cannot find a loop in node B, so we write down 0. There is also not a connection from B to C, so that's why we put a 0 in the matrix. We write a 1 in our matrix because we can find a connection from B to D. There's also a connection from B to E, so that gives us a 1 in the matrix. In the third column, we start from node C. Now we find 2 connections from C to A because the arrow indicates the right way. There are no other connections that start in node C, so we write down 0 every time. We will take the same steps for the connections that begin in node D. We just have to pay attention to the connection between A and D. There is no connection from D to A, as we can see by the direction that the arrow indicates. We cannot find any connections from D to C, to D, are to E, and because of this, we fill in zeros. In the last column of the matrix, we write down two numbers. There is a connection from E to B, and there is a connection from E to E. We can find a loop and not E. All the other elements in our column are 0. So now we have completed the adjacency matrix of this graph. Now I just want to make a few little remarks. In the exercise we have just completed, we have a 5 by 5 matrix because of the 5 nodes in the graph. But if there are 4 nodes in the graph, the matrix will be 4 by 4. Or it will be 3 by 3 if the graph has 3 nodes. All the elements on the main diagonal represent a loop from the graph. In our matrix, we can see one element in the 5th column. This means that there is a loop and not E. You can use this method to check your exercise. In this matrix, the biggest number is 2, because there are 2 connections between A and C, but there is no limit to this. It is possible that there are 3, 4 or more connections between 2 nodes in the graph. Now we can start on the second kind of matrix, the transition matrix. A transition matrix is a matrix that describes how a situation changes over time. This is our exercise. A pizza shop sells pizzas with different bottoms. A crispy bottom, B, a bottom with cheese, and a pan-fried bottom, C. After a quarter, there are customers who still choose the same bottom, and there are customers who choose another bottom. Of those who chose bottom A, 80% still chooses this bottom the next quarter. 12% switched to bottom B, and 8% to bottom C. Of those who ordered bottom B, 75% choose this bottom again, 15% switch to bottom A, and 10% to bottom C. Of those who chose bottom C, 90% choose this bottom again, 70% switch to bottom A, and 3% at bottom B. Currently, 45% of customers opt for bottom A, 25% for bottom B, and 30% for bottom C. Question A. How many percent of these who chose bottom A still buy a bottom A pizza within 2 quarters? What is the distribution of 3 quarters? Is question B. Let's start with the first question. To solve this problem, we need to write down the graph. Here, we will write our data schematically. To know which numbers you have to write, we need to take a look to the exercise again. Of those who chose bottom A, 80% choose to this bottom again the next quarter. 12% switches to bottom B, and 8% to bottom C. Of those who order bottom B, 75% choose this bottom again, 15% switch to bottom A, and 10% to bottom C. Of those who chose bottom C, 90% choose this bottom again, 77% switch to bottom A, and 3% to bottom B. The next step is to create the transition matrix. First of all, you need to write from and above the matrix and to next to the matrix. Above the first column, you have to write A. Above the second column, we write B, and above the last column, we write C. Do the same thing, but now with the rows. Take a look at the question. You need to write the data now at the right spot in the matrix. We will go again. 80% who chose bottom A still choose bottom A the next quarter. 12% switches to bottom B, and 8% to bottom C. Of those who ordered bottom B, 75% choose this bottom again, 50% switches to bottom A, and 10% to bottom C. Of those who chose bottom C, 90% chose this bottom again, 7% switch to bottom A, and 3% switch to bottom B. Now we take a look at question A. How many percent of those who chose bottom A pizza will be buying a bottom A pizza within 2 quarters? We have a first possibility. A person who chose bottom A will be buying The next quarter, also a bottom A pizza. This means that we multiply 0.8 and 0.8. That gives us 0.64. The second possibility is that someone buys a pizza bottom B next quarter and then goes back to pizza bottom A. That gives us a multiplication but from 0.12 and 0.15. That gives us 0.018. The third and last possibility is that someone who buys this quarter pizza A, the next quarter a pizza with bottom C, and then goes back to a pizza with bottom A. That gives us 0.08 by 0.07, which gives us a 0.0056. I'll show you a schematic representation. The first possibility gave us 0.64. The second possibility was 0.018. And the third possibility was 0.0056. We need to make the sum of this. This equals 66.36%. Question A took us a long time to calculate, but actually we can solve this in one step. The short way was to multiply m by itself. M times m equals m squared. Take a look at the solution. The last thing you need to do is to read the answer in the matrix. The answer is an element in the first row and the first column. We use the formula m to the power n, with n is a certain amount of time. To solve question B, we need the current distribution of the customers. Currently, 45% of customers opt for bottom A, 25% for bottom B, and 30% for bottom C. We can write this data in a column matrix with 3 rows, like this. To know the distribution of the 3 quarters, you use this formula. The transition matrix raised to the power of 3, because 3 quarters, and this multiplied by the initial situation matrix. We solve this with our calculator. This is the distribution. The distribution of the 3 quarters is as follows. 38% opt for bottom A, 24% opt for bottom B, and 38% opt for bottom C. Now we have arrived to our third kind of matrix, the Leslie matrix or the population matrix. A Leslie matrix describes a situation that changes over time. Often, when the words birth or survival are in problem, you use this kind of matrix. We make a little remark over here. We will be talking about the Leslie matrix, but the word population matrix is equally good here. We now take a look at our exercise. Consider an insect species with the following characteristics. Survivability. 1. 50% die during the first year of life. 2. 25% survives the second year of life. Third, no animal is older than 3 years. Fertility rate. In their first year of life, so between the age of 0 and 1 year, the insects do not have any babies. Between 1 and 2 years, they have an average of 2 babies. Between 2 and 3 years old, they get an average of 3 babies. Numbers in the initial situation. There are 50 insects between 0 and 1 year old. There are 30 insects between 1 and 2 years old. There are 3 insects between 2 and 3 years old. Put these data in a matrix and calculate what the situation will be after 1 year and after 5 years. To clarify the situation with the fertility rate and survival rates, we draw up a graph. We add the chances of survival. 50% dies during the first year of life. That means that 50% also survives the first year of life. We can also write 50% as 0.5. So we write down 0.5 from 1 to 2. 25% survives the second year of life. We can also write 25% as 0.25. We write 0.25 from 2 to 3. No animal is older than 3 years. This means that our graph stops at age category 3. Now we look at the fertility rates. In the first year of life, the insects do not have any babies. So we don't have to draw a loop that goes from 1 to 1. Between 1 and 2 years, they have an average of 2 babies. So we write down from 2 to 1, 2. Insects that are in the second year of life have babies, and those babies are in the first year of life. Between 2 and 3 years old, they have an average of 3 babies. So we write down 3 to 1, 3. Insects that are in the third year of life have babies, and those babies are in the first year of life. We start by writing down our matrix M with the age categories above and next to the matrix. We also write from and to above and next to the matrix. For example, we go from age category 1 to age category 2. For the age from 0 to 1 year, we note the Roman letter 1. For the age from 1 to 2, we note Roman letter 2. And for the age of 2 to 3, we note the Roman letter 3. We can stop at 3 because no insects are older than 3 years. Now we read the exercise and see that 50% die during the first year of life. This means that 50% are older than 1 year. We can also write 50% as 0.50. We go from age category 1 to age category 2. As a second point, we read 25% survives the second year of life. This means that 25% goes from 2 years to 3 years. And 25% can also be noted as 0.25. Finally, we read that no insects are older than 3 years. So we just filled in the chances of survival. Notice that these are just below the main diagonal. Now we look at the offspring. We read that the insects do not have offspring between 0 and 1 year. So we note a 0. Between 1 and 2 years, they have an average of 2 babies. So we note 2 in the first row in age category 2. This means that going from age category 2 to 1, because a little one that has just been born in between 0 and 1 year. At last, between the ages of 2 and 3, insects have an average of 3 babies. So in the first row in the third age category, we note 3. Notice that fertility rates are always in the first row. But what do we write in the other places? Well, from age category 2, no insects can go to age category 1. Insects, just like humans, cannot undergo rejuvenation. And from the first category, no insects can go to the third category. They cannot skip an age range. This applies to all the other places in the matrix, and for this reason we write 0 in the empty places. Now we set up the matrix associated with the initial state K0. So we look at the numbers from the current state. For this we look at our text. So we see that there are 50 insects between 0 and 1 year. So we write 50 on the first row. We do the same for the other 2 rows. 30 insects are between 1 and 2 years old. In age category 2, we write 30. 20 insects are between 2 and 3 years old, and we write this in age category 3 in row 3. This matrix associated with initial state has been established. You are asked to outline the situation in 1 year. To do this, we multiply matrix M by the matrix of initial state K0. We perform this operation with the graphing calculator and we get the matrix K0 as a result. So what do we actually see? The power that stands at matrix M is 1, and so we get a matrix K1. We can therefore apply a formula here, namely this one. We formulate an answer sentence. After 1 year, there are 120 insects between 0 and 1 year, 25 insects between 1 and 2 years, and 7 insects between 2 and 3 years. Take a look at the way we finish here. With insects, animals, or people, we never round up, but down. We have 7.5 in the third category. But this is of course not possible. We cannot have a half insect, so we round to 7 here. Then we were asked to outline the situation in 5 years. So now we have to take the matrix M 5 times and multiply it by the initial state, namely K0. We can calculate this with a formula from the previous slide, namely this one, where n equals 5 because we calculate the situation after 5 years. We perform the operation with a graphical calculator and we get the matrix K5 as a result. We formulate a response sentence. After 5 years, there are 165 insects between 0 and 1 year old, 58 insects between 1 and 2 years, and 17 insects between 2 and 3 years. Take a good look at the way we finish here. Just like before, we cannot round up here either. We round 165.9375 to 165 and so on. So we saw every kind of matrix that we would like to introduce to you. Thank you for listening. Bye-bye.